Look out into the darkness. Take a moment and truly consider the scale. Everything you can possibly see, every star, every nebula, every distant galaxy captured by our most powerful telescopes, all of it fits inside a vast spherical volume. This sphere, centered on us, has a radius of about 46 billion light-years. That's our observable universe. But it's crucial to understand. This isn't the whole thing. It's just the part whose light has had enough time, since the dawn of the cosmos, to travel across expanding space and finally reach our eyes. Beyond that horizon, space doesn't simply stop. Our view does. And this leads to a question that is simple, haunting, and deeply scientific. What lies beyond the edge we can observe? We have a horizon for two fundamental reasons. The universe has a finite age, about 13.8 billion years, and the speed of light is finite. In the time since the Big Bang, light from the most distant objects has been journeying towards us. But it's not a simple race across a static stage. The stage itself, the very fabric of space-time, has been expanding. As ancient light fought a stretching, growing distance to reach us, its wavelength was stretched, redshifting it. If you draw our past light cone through space-time, tracing back all the paths of light that can reach us, you get a glowing shell, today's cosmic horizon. Anything farther than that is perfectly real, but it is, for now, causally disconnected. Its signals are still en route, battling an ever-expanding metric to cross the cosmic sea. So what created this immensity? Our leading theory is cosmic inflation. In the first fraction of a second after the Big Bang, the universe likely underwent a period of hyper-accelerated expansion. A tiny subatomic patch of space was stretched unimaginably fast, smoothing out wrinkles and enlarging it to a scale far, far beyond what we can ever hope to see. This means there's almost certainly more universe outside our horizon, vast regions that look much like ours, filled with galaxies and stars, governed by the same fundamental laws of physics. They are forever beyond direct contact, not because they are infinitely far, but because the space between us continues to grow faster than light can cross it. What shape is the whole? All of our precision maps of the cosmic microwave background tell us that, on the largest scales we can measure, space is geometrically flat. The angles of a cosmic triangle add up to 180 degrees. But this flatness is only confirmed within tiny error bars. And critically, geometry alone doesn't fix topology. A flat sheet of paper can be rolled into a cylinder or twisted into a Mobius strip without changing its local geometry. Similarly, our flat universe could be truly infinite, stretching on forever. Or it could be finite yet unbounded, like a higher dimensional analog of a wraparound video game screen. If you traveled far enough in one direction, you'd end up back where you started. If the universe has such a topology, it must be so vast that any repetition hides far beyond our observational reach. So, what actually lies just beyond our horizon? The most straightforward, scientifically conservative answer is more of the same, more of the cosmic web, the intricate lacework of galaxy clusters, filaments, and vast, empty voids that characterize the universe we know. The same elements forged in the same types of stars, the same forces of gravity and electromagnetism, the same story of stars being born, living, and dying. It's a humbling thought. The unfamiliar is likely just the familiar, unseen. The edge of our map is not the edge of the world. It's simply the point where our light has run out. The regions beyond are not a different reality, but a continuation of our own, playing out in darkness, waiting for a light that will never reach us. Our limits are hard limits. As we look farther out in space, we look further back in time. But we can't look back forever. Before about 380,000 years after the Big Bang, the universe was a hot, dense fog of ionized plasma, completely opaque to light. Photons were trapped, endlessly scattering off free electrons. We can see only the moment the universe cooled enough for atoms to form and light to break free. This is the cosmic microwave background, or CMB. It's the universe's baby picture, a wall of light from the last scattering surface. This also introduces a fundamental limit called cosmic variance. With only one sky to sample, our precision on the largest scales is forever capped. But could we ever peek behind this curtain of light? Perhaps. Future probes might not rely on photons. Primordial gravitational waves, ripples in spacetime itself, generated during inflation, would travel unimpeded from the very first moments. Detecting them would open a window onto the birth of the universe. Similarly, a cosmic neutrino background, a sea of ghostly particles that decoupled from matter just 1 second after the Big Bang, would carry information from an even earlier epoch. These are monumental technological challenges, but they offer the tantalizing possibility of pushing our boundary of knowledge, even if the horizon of light remains. And what about more exotic possibilities? Here we enter the realm of speculation, but speculation guided by physics. Some models of eternal inflation suggest that our universe is just one bubble in a vast, frothing multiverse. In this scenario, inflation never truly stops, but continues to spawn new bubble universes, each potentially with different initial conditions, different amounts of dark energy, or even slightly different fundamental constants. Other theories imagine cyclic or ekpyrotic histories, where our Big Bang was not a beginning, but a collision between higher dimensional membranes, a cycle of expansion and smoothing that repeats endlessly. These are serious, mathematically grounded ideas, but direct evidence is scarce and perhaps impossible to obtain. For now, they remain tantalizing possibilities, not conclusions. The story of our horizon has a chilling epilogue. Our future horizon sharpens and closes in, thanks to the mysterious force we call dark energy. This energy is causing the expansion of the universe to accelerate. As a result, distant galaxies are not just receding, they are speeding away from us faster and faster. We can watch them fade redder, their light stretched to wavelengths beyond detection. Eventually, they will be receding so fast that any light they emit from that point on will never be able to reach us. An event horizon forms on cosmic scales, a point of no return. The farther future of our universe contains less to see, though not necessarily less to understand. We are living in a brief, privileged era where we can see the most. So why does any of this matter? Because horizons teach us humility, and more importantly, they teach us method. They force us to be clever. We infer the unseen by meticulously studying the patterns in the seen. We look for the statistical fingerprints that the vast, unobservable universe leaves on the part we can observe. Subtle correlations in the distribution of galaxies or faint temperature variations in the microwave sky. We can't sail past the boundary, but we can measure its imprint with extraordinary care and let evidence, not desire, sketch the contours of what lies beyond. And here's how we do it. We map the precise locations of millions of galaxies to trace the faint ripples of baryon acoustic oscillations. We use radio telescopes to chart the distribution of 21-centimeter hydrogen gas across cosmic dawn. We scrutinize the polarization of the CMB for hints of primordial gravitational waves from inflation. We time the arrival of standard sirens, gravitational waves from merging neutron stars. Each of these methods adds a crucial shard of evidence, tightening our constraints and refining our picture of what we can't directly see. New observatories like the Euclid and Roman space telescopes and the upcoming square-kilometer array are designed specifically to push these measurements to unprecedented precision. The picture is sharpening. Within our horizon, the model of precision cosmology ties the universe's age, composition, and history of growth into a single, coherent story. Beyond it, the theories of inflation and the observed flatness of space hint at an immensity that defies easy comprehension. The edge of what we see is not the edge of what exists, and that gap, that tantalizing void in our knowledge, is where curiosity does its best and most important work. Our horizon is a boundary of knowledge, not a boundary of reality. The universe almost certainly extends far beyond the reach of our light, and we are steadily, patiently learning how to read its echoes in the data we can collect. It is a profound reminder that we are part of something far grander than we can ever fully perceive. So keep looking up. Our map is partial, by design, and that is exactly why the journey of discovery continues.